So hello everyone and welcome back to Hope Coaching Institute Private Limited, and this is the second part of theory of thermodynamics. So in the previous lecture we were basically understanding that what is thermodynamics all about and what are thermodynamic processes. So in this lecture we will be studying mainly two topics and we will be deriving them also. So I am taking the very first topic, which is work done in an isothermal reversible process. So we just have to calculate that what will be the value or the general formula for work done in an isothermal reversible process. So we are considering a system in isothermal conditions, which is showing reversible expansion of an ideal gas. And if it is showing some expansion, then there will be a change in volume also. So first of all, the process is isothermal. We have to remember this thing. Isothermal means at constant temperature. Secondly, it is reversible. And thirdly, the thing which I am writing is expansion. So the gas is expanding also. Since there is an expansion, so there will be a change in volume. Let the change in volume will be, we are supposing it to be dV. And obviously the gas which we have supposed is an ideal gas, which follows the basic equation PV equals nRT. Now, since the gas or the system is under isothermal conditions, so delta U will be equal to 0. Why? Since U is a function of temperature, and since U is a function of temperature, so there will be no change in U. U is internal energy. Since the process is being carried out in isothermal conditions, which I earlier said that this means at constant temperature we are calculating the work. So there will be no changes in U because U is a function of temperature. So as the temperature will change, U will give out a value, new value. But no value will be given out in this case since the process is isothermal. So we have to remember this thing, delta U is equal to 0. Secondly, according to first law of thermodynamics, delta U equals Q plus W. So since delta U is equal to 0, Q becomes equal to minus of W. For small amount of heat absorbed or evolved, let this be dQ, and then small amount of work will be done, then let this be dW. Since this work is PV work, so dW is equal to minus of PdV, the conventional basic formula which I took in previous class of this chapter. So just substitute its value. This becomes minus of PdV, and finally dQ gives us a value of PdV. This is the value for dQ. Now, since the gas is expanding, I have written here, we are taking the case of expansion of a gas. So in this case, let the volume be changed from V1 to V2. So V1 will be the initial volume and V2 is the final volume, and this is a process in which expansion of gas is taking place. Expansion of gas. So we have to calculate the work done, total work done, small amount of work done we have small amount of work done, that is equal to minus of PdV. To calculate total work done in the whole process of expansion of the gas, we have to substitute the value of TW, which is minus of PdV. Limits will be of that variable before which D is written. So this D denotes the differentiable part. So D is written before the variable B. So we will take the values of volume B, and its values are V1 to V2. So we know the ideal gas equation is PV equals nRT, and from here we can take out the value of volume. Volume equals nRT by P. So we just have to substitute the value of, and the value of P can also be taken out of this. P equals nRT by V. So instead of putting the value of V, we should put the value of P in this. So if we take this value and substitute in the formula, this was from V1 to V2, and just substitute the value of pressure, that is nRT by V dV. Now, number of moles for a particular amount of ideal gas, the universal gas constant, and the temperature, all will be temperature will be constant because the process is isothermal. R is a constant value, we all know this, and the number of moles for the particular amount of gas taken will also be constant. So this comes out to be nRT. Now the part that is to be integrated is dV by V under the limits V1 to V2. Now dV by V, or the integration of dx by x, comes out to be log to the base e, or natural log. So this is nRT log to the base e of V under the limits V1 to V2. So let's just continue with this. Okay. So continuing with this equation, we are having integration of dW will give us W. So I'm writing W equals nRT log to the base e of V1 to V2. This was our last equation that we have derived. Now we can also apply the limits, upper limit minus lower limit, log to the base e V2 minus log to the base e V1, upper limit minus lower limit. So we might be knowing the property of log A minus log B, that equals log A by B. So log A minus log B can be written as this, log A by B. So this is log to the base e V2 by V1. So this is the formula for work done in terms of natural log. Now natural log of x, or log to the base e of x, is equal to 2.303 of log x to the base 10. So we can also change this log to the base e to the base 10 by multiplying it by 2.303. and this comes out to be, and yes, I think I'm missing that negative sign. Negative sign was also there. You can see from here, the first equation, very first equation. Here, minus of PdV was written, and we have substituted the value of pressure. So negative sign should also be continued accordingly. So please take care of that. So the final formula becomes, now we are converting log to the base e to log to the base 10, and this equals minus 2.303 nRT log to the base 10 V2 by V1. This is the final value for work done in an isothermal reversible process. Okay, so in short, what do we have to do? Let me tell you again. You just have to use the formula for dW, that was equal to minus of PdV. Substitute the value of pressure from PV is equal to nRT equation, which comes out to be nRT by V. Take out the constants outside, there they are nRT, constants will be outside, and you just have to integrate dV by V, and hence you will derive your formula. So this was for isothermal reversible process. Now the second topic which we will be taking is work done in an adiabatic reversible process, a process that is adiabatic and reversible. Now the process that is adiabatic in nature shows that there will be no change in heat. Heat will be taken as a constant value. So changes in heat will be equal to 0. Such a process is called adiabatic process. Now from first law of thermodynamics, du equals dq plus dw. Put dq equal to 0, and hence we derive the value of du equal to dw. Du equal to dw. So let this be the first equation. Also, du equals ncv dt. You might be knowing about this, or we can derive this in some other class. Cv is the, what is Cv? Cv is the heat capacity at constant volume. So heat capacity is basically, I'm just giving it the definition. Heat capacity is basically the amount of heat required to raise the temperature of any substance by 1 degree Celsius. So the amount of heat required to raise the temperature of any substance by 1 degree Celsius at constant volume denotes Cv. If we remove this line of constant volume, then C is the symbol, which is the heat capacity. So since we are talking it at constant volume, so C becomes Cv. Is it okay? Okay. So du becomes equal to ncv dt, and we just have to put this second equation value of du in first equation. So ncv dt becomes equal to dw. Okay. We also know the Mayor's formula. Mayor's formula that relates heat capacity at constant pressure and heat capacity at constant volume by R. The difference of Cp and Cv equals R. R is a universal gas constant. Cp is heat capacity at constant pressure, and Cv is heat capacity at constant volume. So let this be equation number 3. Now divide equation 3 by CV. So the equation becomes Cp by Cv minus Cv by Cv equals R by Cv. So Cp by Cv is called the Poisson's ratio. Poisson's ratio. So this symbol is called gamma. So we just have to substitute Cp by Cv by gamma. So this becomes gamma minus 1, that is equal to R by Cv. And Cv, the value of Cv comes out to be R upon gamma minus 1. So let this value be the equation 4. And now we will substitute this in the value of work done, which we have calculated. dW was equal to NCV/dt, and just substitute the value of Cv that you have obtained. So let me clear the screen first. So just substitute this. So what will be the value of dW now? dW comes out to be R by gamma minus 1. We have substituted the value of Cv here, and N dt. Okay, so now just to calculate total work done, we previously also we have done in isothermal reversible process also, we have to integrate it similarly as we have done earlier. So just do the integration to calculate total work done. So integrating both sides, you will be knowing that N R gamma is also a ratio, minus 1 is also a number. So these are all are constants, and dt will be integrated, which is the temperature. So let the temperature change be from T1 to T2. Since this is an adiabatic process, so changes in temperature can be there, but there will be no change in heat. dq will be equal to 0, but temperatures can change. So in the previous case, temperature was constant. So let us just integrate this and derive at our answer. So integration of dW will give us W, and this will be equal to NR by gamma minus 1, and integration of dt is T under the limits T1 to T2, and the final formula becomes work done for an adiabatic process NR by gamma minus 1. You might be knowing that gamma is equal to Poisson's ratio, as I have told you earlier also, and upper limit minus lower limit. So this will be the formula for work done in an adiabatic process. And let me tell you one more thing, that you can see that there is a temperature difference which is playing a vital role here. So let me tell you that if T2 will be greater than T1, then work done in adiabatic reversible process will be positive. So if work done will be positive, then that means that work is done, some work is done on the system. To understand this line, you must watch the previous lecture. Work is done on the system. And second is, if T2 is less than T1, then work done will be negative. You can see in the calculation also, if T2 will be greater than, the subtraction sign is there between them, so magnitude of negativity will be high and work done will calculate out to be negative. So work done, your work is done by the system, So these are two conditions for this very formula, and let me help you revise this again. So what we have done in this, firstly we have applied first law of thermodynamics, which was du equals dq plus dw. We know that since the process is adiabatic, so dq will not be there and du will be equal to dw, and we must be knowing the value of du, that is ncv delta t, or dt, which is equal to dw. After this, we applied the Mayer's formula, Cp minus Cv equals R, and from that we calculated the value of Cv. Then we have to substitute the value of Cv in this equation, and then we have to integrate both sides. This was the process for work done in adiabatic process. So two things we have done today. There are some other results also which I am writing here, which you may remember, some other results which you don't need to revise in derive in chemistry, but yes, there are some results that you must remember, and these results are for adiabatic expansion. Okay, so like first equation, which is very important, is PV raised to the power gamma is a constant. PV raised to the power gamma is a constant. Please note that V is only raised to the power gamma, not P also. P V raised to the power gamma is a constant. Next is T raised to the power R. P1 minus gamma is a constant. And third is V raised to the power gamma minus 1 T is a constant. So if not all of three, but first equation at least you must remember very well. Okay. So today we have calculated two basic derivations, and in the next class we will continue with some numericals now related to these derivations and the previous lecture also which we have done. Okay students, please share the video, subscribe the channel, and thanks for watching.